So good morning, everybody. I would like to thank Oxhill to have a chance to present in front of you. We are a small company based in the Czech Republic, and we started our collaboration with Oxhill actually 6 months ago. I will tell you first something about our company, and then a few ideas we have and we are exploring together with Oxhill about incorporating single-wall carbon nanotubes into the nanofiber-based materials. First, I would like to start with explanation a little bit about nano, because I speak to a lot of people, and a lot of people tend to put nano into one box, you know, and it's very important to know that nanomaterials have different shapes, different structures, and obviously, you know, nanotubes, this is all about here, but we have nanoparticles, nanorods, nanodots, nanocrystals, nano everything, nano different shapes, and I'm going to be speaking about nanofibers. Also, definition of nano is quite complicated because there is very difficult definition about what nano is, but let's this leave for later. So my company is actually working on development and production of nanofiber materials. There are two technologies which are used for development and production. First of them is electrospinning. Electrospinning is very old and well-known technology. We are using the electrospinning only for R&D purposes because we are able to make finer fibers. But for industrial production, we have selected a technology which is called centrifugal spinning. And this technology was selected on behalf of our experience as a more appropriate for mass production of nanofibers. Today, we can actually make nanofibers from solutions. I will explain later. And we are preparing the technology for melt spinning. So what we do, we focus on development custom-made ceramic nanofibers on inorganic nanofibers, custom-made polymeric nanofibers, and we are able to develop new materials with nanofiber structure and upscale it to the production. So that's actually what we do. Nanofibers are just material. You need to find application for it. So it's nice to have nanofibers, but where to commercialize, where to get the money out of it. So we have to actually collaborate on development of applications and products. This is very important. And what we have learned throughout our history, we are a 7-year-old company, we have to continuously work on development of production technologies as well. Because the technologies which are available on the market at the moment, they don't work very well. So we actually spent 4 years optimizing so-called industrial line for production to make it working. So we got our own know-how on technology, our own patents. Besides production and development, we offer customers analysis to characterize powder-like materials. So I was speaking about the inorganic nanofibers. We actually call them NNF serum. We are able to make different oxides into nanofiber structures, either in powders or cotton-like structures. And if we speak about ceramic nanofibers, we speak about titanium dioxide, silicon dioxide, zirconium dioxide, and many others. The applications for those materials are quite wide. I see the highest potential for those materials in energy storage, battery separators or anode or cathode materials, catalyst support materials, and composites. Actually, the ceramic nanofibers was the initial idea of our company to start and produce those type of materials. But during the time, our customers or partners were coming to us and asking if we could produce polymeric nanofibers. So we have started development of polymeric nanofiber membranes, which are mainly used in filtration or separation processes. And with new technology, we are able to make like 3D, we call it 3D cotton-like structures of nanofibers, which is the unique structure which can be used for new applications. If you speak about polymeric nanofibers, we speak about polyurethane, nylon 6, PVB, PCL, PAN, and other special polymers. So this is how actually the fibers are made. It's centrifugal spinning. It's quite old technology, broadly used for glass fiber production, for example. We have just added a little bit of physics and chemistry to the process, and we are able to make nanofibers by actually spinning solutions by centrifugal forces through nozzles, and create interesting structures. So the technology we are using is 17 times more efficient than electrospinning. It's much easier to control production parameters. It gives us possibility to produce 3D nanofiber structures, which is not possible with electrospinning. It's possible to produce nanofibers from melt. It's more ecological and much more efficient, more economical and ecological production of inorganic nanofibers. For example, with electrospinning, if you make nanofibers, you need electrically conductive solvent solution, and you use ethanol as a solvent. If we produce nanofibers with centrifugal spinning, we were able to replace ethanol with water. And if give us the technology variability, so we can actually construct and design different type of technologies, production lines. Those are the problems we are actually solving during the development and production. Those are just like droplets which are created by splashes during the production. We got beads, ropes, and splashes. You know, those are defects in the structure, in the nanofiber structure, which creates and very often are unwanted, but some of them are wanted as well. For example, if we control the amount of droplets in the membranes, we can help better adhesion to substrate or whatever. So this is actually how ceramic nanofibers are made. This is a step-by-step process description that in the first step, we prepare polymer solution. We actually get base polymer. We dissolve it in solvent. We add precursor in a form of salt or colloid suspension. We mix it together and we prepare solution of certain concentration and viscosity. Then we use centrifugal forces to spin, we call it precursor fibers. And the next step is calcination. We have to put precursor fibers into the oven, apply specific temperatures to actually burn out the base polymer, which you need to create fibers, and to let the precursor oxidize on the fiber structure into the nanofibers. And by this, we get cotton-like structure materials, and we can then post-heat it by milling or prepare dispersions and so on. The fiber diameters, I speak about nanofibers, but we rather have sub-micron fibers with very high surface area. So the fiber diameter is somewhere from 250 up to 800 nanometers. They are a little bit thicker than fibers made by electrospinning. The length is in millimeters or centimeters. We can mill it down to a few microns if customer requires so. Fiber structure is powder or cotton-like material, and the crystal structure actually and the surface area, it very much depends on final calcination temperature and on the calcination process. The advantage of this process is actually that we can functionalize nanofibers with high surface area with some active materials, nanoparticles, for example, silver, palladium, platinum, whatever. We can add the particles directly within the step 1 into the solution and spin it. So after calcination, the active particles are incorporated in the structure of the fiber. Because we speak about mesoporous fibers, they are accessible even though if they are inside of the structure. So this is about ceramic nanofibers. It's a little bit easier to make polymeric nanofibers. You basically have, again, polymer solution, which you prepare by dissolving polymer in solvent or in combination of the solvent, because the creation process for nanofibers is based on evaporation. So we sometimes combine 2 or 3 different solvents. Then we spin the nanofibers by centrifugal forces again. The main challenge actually for polymeric nanofiber membranes is its post-treatment. Lamination process, because the fibers, the membranes are quite fragile, so you have to protect them. Basically, to make membranes, you need substrate, which runs through the machine. You deposit fibers on the substrate, and very often, or for all of our products, we have to cover the nanofibers with additional layer in order to protect them. Again, those polymers can be functionalized by different nanoparticles. We very often use silver nanoparticles to add antibacterial function for filters, for example. And we can add different substances into the fibers. So if we make filters, we can add, for example, vanilla essentials into the solution, and then the filters actually smell nice, for example. So we actually provide services on development. We are partners for several projects, either European funded projects or projects funded by our customers. We can actually run our own R&D projects, but all the idea about my company is that we develop every material and every application with specific partner for their specific needs. Those are actually the products already available on the market. Just to show you that we really can do it. We got 5 patents granted in last and this year. We've got 5 commercial products in the market. One of them is HEDA. Let's take it from the left. Yeah, it's left from your side. It's the patented 3D lithium-ion battery, which was designed and developed by one Czech inventor. And we use ceramic nanofibers to create a ceramic separator inside the battery. And why ceramic nanofibers? Because they can actually add extra function to the battery. The first function is the safety. You can operate the battery up to 500 degrees of Celsius. So this is actually a big advantage. We are not speaking about small batteries. There are large batteries or big batteries. The company HEDA has just started building his gigafactory in the Czech Republic last month. BreeSafe are like antibacterial respirators. This is new product which we plan to introduce to the market at the beginning of 2018. Again, it's antibacterial nanofiber-based membrane which is used for creation of breath masks. We have developed a membrane for swimming pool filters together with Astral Pool. Or actually, Astral Pool is selling the filter, but we've developed it with one of the Spanish company. And the filter actually has several advantages against sand filter. We have better filtration efficiency, higher flow rate. We have much smaller and lighter equipment. It's like 3 times smaller and lighter. You actually need much less water to clean the filter. If you are cleaning sand filters, you consume a lot of water which you have to release to the drain. So this is like new type of product. It was designed for swimming pool filtration, but now we are actually testing this product for other applications as food product filtration or industrial wastewater treatment. And Riftelen is our membrane which is used for food product filtration in desk filters. And it has several advantages against the cellulose filtration desks. Better filtration efficiency, much higher flow rate, it's flexible, it can be cleaned and used several times. So those are actually applications. And the last in the corner, it's, you don't see, but at the tip of the analytical tips, there is nanofibers, ceramic nanofibers, which are used for sorption of special peptides within the analytical work. So we can actually, thanks to high surface area, we can use the fibers as a sorbents. And now let's go to the point why I'm here. When I first met guys from Oxial, we were discussing where we could use their product within our development, and it's something absolutely different from what you have seen here. Maybe that was the reason why they offered me to present here, because those are like new early stage ideas and development. But the idea is to make electrically conductive filtration membrane or electrically conductive ceramic nanofibers, catalyst support for tubal deposited with palladium. This is a project which has at the moment nothing to do with nanofibers, but it came to the point when we were discussing applications. We have one university and commercial partner who is actually planning to use this material. Why? Electrically conductive membrane. There is a process which is called electroporation. We have patent on electrically conductive membrane, which is prepared by centrifugal spinning and chemical post-treatment of the membrane. So we can do it. The electroporation is process of inactivation of bacteria by electric field during the filtration. Today, if you want to remove bacteria from water, you have to use either chemicals or very fine filters. Very often, you filter out a lot of good stuff from mineral water, for example, in order to remove the bacteria, to get the sterility. So, with nanofiber electrically conductive membrane, we have studies and first results from the electroporation process that we can remove up to 99.97% of bacteria by adding electric field to the membrane during the filtration, which is quite amazing. The problem is that if we coat electrically conductive coating on the fibers, they are washing out. The coating is washing out. The idea of using carbon nanotubes is to have them embedded in the structure of the fiber, so they do not wash out. So they stay. We can use the filter for a longer time. Or using the membranes as a sensors. It's a very interesting topic, and we speak about chemical sensors. Electrically conductive NNF ceram. Ceramic nanofibers mainly used in cotton-like structure. We can actually use paper-making technology to make filters from nanofibers, ceramic filters, so they can withstand chemically and thermally. Having them electrically conductive opens new horizons, for example, for regeneration. If we use the filter, we functionalize it with catalytic nanoparticles, then we have catalytic filters, which needs to be regenerated. So we could actually heat up the filter is the idea. I don't know if it's going to work, but to regenerate it very easily. Or anode or cathode materials for batteries, fuel cells, or energy harvesters. And catalyst support of tubal by palladium, it's a concrete requirement from one of our industrial partners. They want to use this combination for polyethylene terephthalate synthesis. I don't know what does it mean, but they say it's potential. How did we do it? I was explaining earlier that we can add single-wall carbon nanotubes directly into the spinning solution. either if we speak about membranes or ceramic nanofibers. So this is the idea: add tubule directly into the spinning solution, so there is no other post-treatment step needed. We have challenged it quite some problems. You see on the bottles the agglomeration of tubule nanotubes, and the reason is that we use quite big concentration. So in the future we need to decrease the concentration of tubule in the solution in order to avoid the agglomeration. This was really first tests, and there is a lot of work in front of us. Catalyst support, chemical deposition of palladium on the surface of single-wall carbon nanotubes, or ALD, that's so-called atomic layer deposition of palladium. Those are like pictures from initial results. Basically, you can see the laboratory spinning tool which we are using for fiber development. It's a simple tool which has a small container and 2 nozzles. And through the nozzles we are spinning out the fibers. We collect them on the collector and then analyze it. Actually, what you see, we used long nozzles or syringes, two different diameters, and what we have experienced, very low fiber production and very low content of carbon nanotubes, because the carbon nanotubes with length of 5 microns find very difficult way to go through the syringes, through the nozzles. So they actually clog the spinneret, and just the polymer went out of the spinning head. We repeated the same process with short nozzles, and you see a lot of droplets, you know, on the paper. So there was very difficult to observe fiber forming process, because it's nozzle-based technology. Here we did some SEMs. We believe the particles on the fibers are single-wall carbon nanotubes. We need to do more tests and EDX analysis. But there is promising way to functionalize the nanofibers with single-wall carbon nanotubes. And here are the ideas to solve the problem. The problems we have observed were very difficult to disperse. It's general problem with single-wall carbon nanotubes, so there is a process which needs to be optimized. When spinning on nozzle heads, it's clogging. And when trying to chemically coat, I was speaking to the partners from the university. They found quite big contamination of the single-wall carbon nanotubes by different catalysts. So if they wanted to deposit palladium, they had to clean and remove all the contaminants from the single-wall carbon nanotubes. Unfortunately, I don't have any pictures from the university, because they were not able to provide it to me before the deadline for presentation. So ideas to solve the problems is to use lower concentration of single-wall carbon nanotubes. This is something we're going to work on. Then to use nozzle-less spinning head. I was speaking about development of spinning technologies. We are working on that, and we have developed the technology which actually is able to produce nanofibers without nozzles. It's several times more productive, and it opens possibility to functionalize the fibers with different and bigger materials, and to remove the contaminants. I was speaking to Oxil yesterday, and they are preparing some high purity materials, so this could be also possibility to work with. And this is the picture of new technology. We are part of the team developing this technology. We are getting back to electrospinning. The electrospinning I was speaking about at the beginning of my presentation is based on DC. So basically you need 2 electrodes to drive the fibers from the polymer solution. AC electrospinning was developed and patented by Technical University Liberec, which is our partner in the Czech Republic, and Cluster Nanoprogress. And actually it's based on AC, so you don't need the opposite electrode to create fiber forming process. So you can, with this technology, which is much higher production yield, does not need nozzles, and does not need opposite electrode. It opens new horizon for manufacturing of new and novel materials. We are part of the consortium. Next year we will be building, we call it AC gun. So it's going to be like a gun which will be shooting the fibers on different substrates or different collectors for many applications. So this is also technology which we will definitely use for functionalization of nanofibers with single-wall carbon nanotubes. And I believe, yeah, that's it. That's it from me. Thank you for your attention.
Thank you very much. Are there any questions from the audience? There are some.
My name is Vladimir Saik, Axial Group. My question is, first question, I guess. Are your polymer molecules oriented in inverse polymer fibers? What do you think?
I'm not a polymer chemist, so I can't say, but I believe so.
I see. Another question is, how do you try to disperse tubule? How do you disperse carbon nanotubes?
By ultrasound. We are using ultrasound. We disperse in a solvent, which we use to dissolve the polymer. So first we actually use a solvent, we add carbon nanotubes in it, mix it in ultrasound, and then dissolve the polymer in this system.
Did you ever try to mix together polymer and carbon nanotubes and do sonication after that?
We haven't tried it, but we can definitely try it because we need to observe more ways how to prepare. You know, the idea is, for example, using master batch of functionalized polymer and then dissolve it. So we can talk about that, and I will appreciate any of your support on this field.
Okay, thank you.
Thank you very much. Any more questions? Ravi?
It's a good training.
Have you tried purified tubule without iron catalyst?
As I said, the purifying single-wall carbon nanotubes is done by a partnering university in the Czech Republic. So as I didn't receive any information from them, I can't say what technique they use for purifying. Sorry for that.
Yeah, I know that the purification is a big thing for the battery industry, as we heard yesterday, and I'm very sure for tests we can supply with the purified version.
Oh yeah,
in an easy way.
Yeah, good,
okay.
Good, perfect.
Thank you very much. So big applause and thank you very much.
Thank you very much.
Thank you.
Cheers.